Measures of variability. Take a look at these graphs, either green or blue. And if you look at the set at the very top that's labeled medium variability and focus on one end of the graph to another, whether you're looking at the green or the blue, you see the link there from one end to the other. And if we call that medium variability, take a look at then the next set that's labeled as high variability. You see that it's still a normal distribution like the top one, but it's spread out a lot more from one end of the graph to the other. There's a lot of variability of data, right? So we would say that that's high variability compared to the one in the previous. And then if you look at the third one, you see it's still a normal distribution, but if you were to look at from one end to the other graph, there's very little variation of numbers. And so we would get a graph that looks very, very thin like this. And we would say that's low variability. So measures of variability then has to do with how much we see the spread to be. So how big or wide is the spread among numbers in a given data. So going back to this table as a roadmap for us, we've talked about frequency distribution and measures of central tendency, where we talked about mode, median, and mean, and how we use different types of averages based on different types of data, nominal, ordinal, interval, or ratio. Now we're talking about measures of variability, which is to say, what is the variation of numbers around the mean, right? If we know what the average is or the midpoint is, what do the other numbers look like around that number? And then the next topic is going to be on correlations. But first, measures of variability. According to this table, we see that there are three different ways that we measure variability. There's the range, that's used for nominal, ordinal, and sometimes interval and ratio data that's skewed, or semi-interquartile range as a measure of variability for skewed data, and then finally variance or standard deviation for normally distributed numerical data. So I would argue that average is not enough in fully describing a set of numbers. For example, data set 1 has numbers 70, 70, 70, 70, 70, and the mean would be 7, and the range is 0, and we define range as the distance between the highest and the lowest. And we see that there is absolutely no variation in this data. Now compare this to the next data set. Data set 2 has numbers 80, 60, 70, 65, and 75. Now, if you add up all these numbers and divide, you would be getting your mean. And surprisingly enough, you get the same mean as this first data set. By looking at the two means, you have no idea if the data sets should look alike or different. And so when you look at the range, which is part of measuring variability, that gives you added information that these two data sets don't look alike at all. Because in the second data set, the range is 20, which is the distance between the highest and the lowest, and that would be the 80 and 60, right? The difference of 20. So that tells you that there's some variation in data set 2. Now take a look at this next data set. Data set 3 has numbers 100, 40, 70, 95, and 45. So you have some huge numbers and some small numbers, and you would expect the range to be much, much bigger. In fact, while the mean is the same as the first two data sets, the range here is 60, the difference between 100, the highest score, and the lowest score of 40. So just by looking at the means, you have no idea what these data sets look like. For all I know, they could all look the same. But here with the range, you can see that there is difference in variability in these three data sets. So variability is measured then by using range or semi-interquartile range or standard deviation and variance. And I put standard deviation and variance together as we will see that they kind of go together, right? So range first is defined as the highest score minus the lowest score. So here's another simple example, 1, 2, 3, 4, and 5. So let's assume that these are our numbers. What would be the range? The range would be the highest score minus the lowest score, which is 5 minus 1, which equals 4. Right? So you would say the range is 4 points. Semi-interquartile range is defined as the average of the distance between two interquartiles, and that's why it's called the semi-interquartile range. Now, this is useful for skewed data, right? So if you have a normal data, you wouldn't calculate for semi-interquartile range. Conceptually then, semi-interquartile range is to look at the graph, right? Such as this. This is somewhat skewed, right? The way we know that is these arbitrary numbers that I put in here, 2, 5, and 10, show that there are numbers at 25th, 50th, and 75th percentile. So there's a graph that's divided into 4 quartiles, right? 4 quarters. And I see that it's skewed because the distance here in one quartile of 3 is different from the difference of quartile here of 5. So it's somewhat skewed. It's not a normal distribution. In a normal distribution, you would find the quartiles to be equal in size. So the idea is you take the size of 2 interquartiles and take the average, right? So in this case, you have one interquartile the size of 3 and the other interquartile of size of 5. So you take the average of that. So you would add a 3 plus 5 and divide it by 2, which gives you 4. And another way to calculate, which uses the formula here, which says score at 75th percentile minus the score at 25th percentile divided by 2, is really doing the same thing. You get the same answer by calculating it this way, but it's a bit easier, where you take the number at 75th, which would be 10, and subtract from that the score at 25th, right, and take the average. So the answer there is 4. So the way that you would interpret a semi-interquartile range is to say that in a skewed distribution, the average size of 2 interquartiles is 4. By itself, a semi-interquartile range may not be very meaningful, but when you begin to compare one semi-interquartile range to another, then it becomes much more informative. So here's the formula: score at 75th percentile minus the score at 25th percentile divided by 2. And that gives you the semi-interquartile range. Let's move now over to normal distribution, right? In interval or ratio data or numerical data that's normally distributed. In a normal distribution, we calculate a standard deviation. Definition of standard deviation is it's the average of how far the scores are from the mean. So it's the average of deviation scores. Well, what does it mean to have deviation scores? When you look at this calculation here and list the scores 2, 3, 4, 5, and 6 on a table and subtract its mean of 4, you have these numbers in the deviation column: -2, -1, 0, 1, and 2. And these measure how far the scores are from the mean. Right? So in other words, these are your deviation scores. Okay? This is how much they deviate from the mean. Well, if we know that standard deviation is the average of how far the scores are from the mean, or the average of deviation scores, then it would be easy to just try to get the average of these numbers, because standard deviation is the average of deviation scores. But we run into a mathematical problem. When you take deviation scores, you see 1/2 of the identical numbers that are minuses, and then another set of positive numbers. So they cancel each other out, and the deviation scores always add up to 0. So this is a numerical challenge, the mathematical challenge, in that we can't take the average of 0. And the standard deviation cannot be 0, because we know that there are scores that deviate from the mean, right? 2, 3, 5, and 6 deviate from the mean. So we know that there's a standard deviation that cannot be 0. So statisticians sat around this and thought, how do we get around this mathematical issue and still be able to take a standard deviation or calculate a standard deviations? So they decided that we would square the deviations. So when you square the deviations, then you lose the minuses, right? So -2 squared becomes 4, -1 squared becomes 1, 0 becomes 0, 1 becomes 1, 2 squared becomes 4. Now, if you were to take the average of deviation squares or square deviations, then you can take the average. So when you have the deviation scores squared, you have the minuses that disappear, right? So you have minus 2 squared, which becomes 4, minus 1 squared, which becomes 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So when you have all these positive numbers, then you can add them up and divide it by the number of scores to get your average, right? So these square deviations add up to 10, so you divide it by 5, and that gives you 2, right? Now, what is that number 2? So the number 2 is the average of square deviations, literally, right? So because it was the average of square deviations. Average of square deviations is your variance. Now, what we really want is not a variance, but standard deviation. And this variance of 2 is a huge number because it's the average of square deviations, and we needed to square them in order to get around this mathematical issue of deviation scores adding up to 0. So then once we have the variance, we want to kind of deflate what's been inflated. So one of the ways to do that is to square root the variance, right? So when you take the square root of 2 in this case, which gives you 1.41, then you have the average of square deviations without the square, right? Because we have square rooted and downsized it, deflated, and made the number be more relevant to our data. So now we have the average of deviations as best as we can get at 1.41. And that's what we called a standard deviation, ST for short. So the way we would interpret this is to say that scores vary from the mean on average by 1.41. Okay? And that seems to make sense because you have one score of 4 and you have one score that's away from the mean by 1 point, another one away from the mean by another, and then these are all negative deviations, and then you have one score away from the mean by 1 point, and one score away from the mean by 2 points, and you got one score right in the middle. So that kind of averages out to about 1.41. And so that's how we calculate for standard deviation. And this is a huge table and undertaking, but the formula looks like this. It follows the same method that we had done earlier. So this kind of calculation, creating a huge table of calculating for variance and standard deviation, we call that the definitional formula because the table kind of lays out what the formula is. And here, the computational formula that I'm going to introduce to you is a lot easier formula to use for calculation of variance and standard deviation. So you see in this formula here, you need to have the sum of x's squared. So we want to square all the x's and total, minus, and this is in parentheses here, the sum of x's, right? That would be 1 total squared over n, right? All divided by n. And of course, when you square root the entire thing, then it becomes your standard deviation. So let's see if we can use the computational formula this time. So with this data, it's the same data we saw earlier. We would need to have the total of x's and total of squared x's. Right? So when we add up all the x's, it becomes 20. And when you add up all the squared x's, right, that would be x squared for each number, you have a total of 90. Right? So in the formula then, you would plug in the 90, the bigger of the two numbers, minus the sum of x, which was 20, squared over 5, all divided by 5. And then it's square rooted for standard deviation. So when you take 20 squared divided by 5 and subtract from 90, it becomes 10 over 5, okay, which becomes 2. Right? And when you square root, it becomes 1.41. So same numbers that we saw earlier. So the symbols we use for variance and standard deviation are such that for the average squared deviation, in the symbol, we keep the squared in there to tell us that that's variance. So the symbol is S sub x squared, right, for the variance. And then it makes sense that for standard deviation, then the notation should not have the squared in it. So the average deviation uses the notation S sub x, okay, 1.41 as the standard deviation. Again, standard deviation, the interpretation is very important. And a typical wording of a standard deviation would be to say the scores vary from the mean on average by 1.41. So how significant is that? If you look at this graph here, this is a standard graph of a normal distribution where with the 0 in the middle, if you go one standard deviation out, that includes 34.13% of the data. And likewise, the same thing on the other side. And if you take the data one step further out by a standard deviation, it adds another percent, 13.59, okay, on either side. And then another standard deviation out would add 2.14, and then the last possible calculation out to 4 standard deviations would add the remaining 0.13%. So all of these percents then would be 50% on one side, 50% on the other side to make it 100%. And so we would say that if we have a mean and a standard deviation, we can pretty much tell what the 68% of the data would be like. In other words, 68% comes from 34%, 34.13% here, and 34.13% here. So it's 68% and then some, right? So if we were to say 68% of the data, then what we're really saying is take the mean, right, and add a standard deviation and subtract the standard deviation, and that should give us the 68% range. If you were to take it another step out, a standard deviation out this way and to the other way, so it's 2 standard deviations out away from the mean, that is what we call the 95.5% range, because then that includes the 13.59 and 13.59 here again. So when all those percentages are added together, that adds up to 95.5% of the data. Interpretation-wise, we would say those two numbers are the range within which we think that 95% of the data will be. And then the further we take out to 3 standard deviations out, it includes 99.7% of the data, and then lastly 99.9% of the data. Formula-wise then, if we have a mean and standard deviation of 1.41, the one we just calculated, for a 68% range, we're talking about taking the x-bar, or the mean, and adding and subtracting 1 standard deviation of 1.41. And then for the 95.5% range, adding 2 standard deviations and subtracting 2 standard deviations. And for 99.7% range, we take them out 3 standard deviations. And for 99.9% range, we take them out 4 standard deviations. So here's a better graph that kind of looks at and tells us the totals from this inside, from the middle, still using the same numbers here. 68% range then would be x bar plus or minus 1 standard deviation, right? So the calculation tells us that the 68% range of scores is between 2.59 and 5.14. So 68%, or the majority of the data, range within these numbers. If you remember the actual data that we used to calculate for the standard deviation and the mean, the scores range from 2 to 6. So this range then includes the majority of the data. 95.5% of the data would be to take the x-bar and add and subtract the standard deviation twice, which gives you a bigger range. And it's a bigger range because this range then includes 95.5% of the data. So this is really useful because even if we don't have the raw data once we have the mean and the standard deviation measures how much scores vary. So using these two numbers, then we can have a very good idea of how much the scores range by calculating the ranges as needed. Let's try another example. Here you see some special symbols here. So mu is called the population mean or the true mean, right? So this is the mean of the entire population. And standard deviation of the population is noted by a Greek letter, small letter s, right? Little circle with the tail on the top. And that refers to the population standard deviation. So in the population, then, we have IQ of 100 as the population mean, and plus or minus 15, right? So using these two numbers, if I were to ask you to calculate for and figure out what the 68% range of IQ is, then you would take the mean, right, x bar, plus or minus 1 standard deviation, right? So that would be 100 plus or minus 15. And when you calculate that, that gives you the range, right? So you say the majority of the people have IQ between 85 and 115, right? So similarly, then you can try the other calculations to come up with the range within which population range in their IQ. So far we've talked about variance of the sample. This is the definitional formula that we've seen before. The only difference there is we used x bar here, and this letter M means M for mean, right? So it's really the same thing here. So we've seen how to calculate for variance, and this is variance of a sample. So what if we wanted to calculate for the entire population? The variance of population then would follow with the formula with a symbol that we saw in the previous slide. You remember that mu, the letter mu, stands for the true population mean. And we see the symbol here, right, that we've seen before. But since it's for variance, it takes on a square, right? So in order to calculate for a variance of population and use the definitional formula, we need to know the true population mean. So unless we study the entire population, we wouldn't know how to calculate for variance of the population, right? Because oftentimes this mu is unknown. So variance of population is something that we normally cannot calculate. So the next best thing would be to estimate it, right? And we estimate the variance of the population using the sample data. And we call that the variance of estimated population. So if you recall the variance formula, definitional, right? It's x minus m, or mean, or x bar. But it takes on this little notation, -1. Right? So that would be the difference, the only difference really between the formulas for variance of sample and variance of the estimated population. We use the variance of estimated population for hypothesis testing because that's an estimate of the population and not a straightforward variance of the sample. So then for the estimated population using the definitional formula, the formula for variance then just takes on -1. And same thing, -1. This is for the definitional formula. And we know that the computational formula is a lot easier. And it does the same thing. Whatever the formula is, we just add -1 to the bottom to get the variance or standard deviation of the estimated population. Everything else remains the same. So here's a page of just summarizing all the different variations, the definitional formula and the computational formula for sample, which is the first column, and for the population, the second column, and we know that for the most part we can't calculate. And for the estimated population, these added -1 feature on the same formulas that you've seen in the first column under sample.